Hello! Today we are going to talk about another format for describing rotational motion in terms of its dynamics and some of the processes that you and I may encounter while studying this topic. So what is rotational motion? In terms of kinematics, we have introduced in our time some concepts that describe it, such as angular displacement, angular velocity, and acceleration. We introduced the relationship between linear and angular quantities, and actually there we analyzed in detail how this phenomenon can be described from the point of view of kinematics. Now the question arises as to how such motion arises at all from the point of view of the forces that act on in terms of the forces that act on the bodies as they rotate. And now let me try and show you in a drawing how a certain object rotates around a circle. In a circle and why it does that. Or for example, we have a stone that was tied to a thread and a person started to spin it, for example, in a vertical plane. After unwinding it to a certain speed, the stone began to describe a circle of some radius, let's say radius r. And in this case, rotation here, we can say that the stone will have a certain velocity, and at any given time, that velocity is tangentially directed. And so there will be a certain acceleration. Why does this acceleration appear? Let's remember again. First of all, velocity in this case can be a variable quantity in direction and in modulus. So there's a certain acceleration which is responsible for the change in modulus of velocity and for the change in direction of velocity. Well, even provided that the velocity and modulus may not change much, but the direction of velocity at each moment of time will be different. And in this case, we are talking about a certain acceleration which is called centripetal acceleration. This acceleration arises once again due to the change in the direction of velocity and is determined by the formula the ratio of the square of the velocity to the radius of the circle on which the object is rotating. But what leads to this acceleration? Well, as you and I know, from the dynamics of motion, acceleration is always due to the presence of a force that acts on the body. And that gives rise to the corresponding acceleration. If we look carefully at the triplet, what force can act on a stone that rotates on a rope? Well, of course, it's the force of the tension of the rope. If that force disappears, if the rope breaks, for example, then of course the stone would start to move in a different direction. And there's no more circular motion. Of course, we can also speak here about the force of gravity, which will also act and participate in this motion, but still it is the tension of the rope that will be responsible for the rotational motion. It is due to this action that we get the corresponding acceleration. And Newton's second law, which we can use here to describe this process, would look like this. The fact that the force that causes this acceleration in this case, acceleration, we can also call it centripetal force, will be determined by dividing the mass of the body by the acceleration that the body has produced in this case. And here the acceleration we have calculated in this way. Of course, we can make a substitution and let's say consider the calculation of this acceleration through some angular parameters because sometimes it is easier to describe rotational motion by angular parameters. So we can replace linear velocity with angular velocity through the following formula. You and I also learned it in the kinematics of motion. Received. And by squaring each of these parts, we get an expression, this expression. By reducing the radius, we get this formula. You can use it as a ready-made formula and in principle. We can write the centripetal force as m times omega squared and the radius. So we have got a value for this force through two velocities. This is through linear velocity and through angular velocity. Either of these formulas will work for you in problems. In addition to these situations, you and I may encounter other cases where there are manifestations of a body moving along a curved path when, for example, you're driving along a road and you go over a bump. Here we can experience a change in our weight as we go over that bump. And these changes are due to the fact that there is an additional force that is added to or taken away from the force of gravity. It's the centrifugal force. And in this case, your weight becomes either more or less. This is all due to the fact that the motion starts to change from straight line to curvilinear, and there are additional factors that will affect your condition. Another example for rotational motion of this type we can also find in space when around a certain object, such as, for example, as the The Earth, for example, a satellite, is traveling in a circular orbit at an altitude of, say, h, and let's denote the radius of the Earth by the letter r. Then in this case, this satellite having a certain velocity, I will make a continuous circular motion, being under the influence of the only force that acts on it in this case is the gravitational force. That is, gravity in this case between the Earth and the satellite plays the role of the same rope that held the stone in this circular orbit. Here it holds the satellite and does not let it fly away into space. At the same time, the satellite cannot fall to Earth because it is moving. In this case, we can use the practice of accepting the transition to a non-inverse reporting system and show that on this satellite, in this case, if we're on the satellite itself, there will be two forces acting on it. And there's the gravitational force of the Earth and the centrifugal force that's trying to throw it out of this orbit. Or in this case, if the satellite is at a constant distance from the Earth's surface, then between these forces we will observe a balance, that is, an equality. In this case, they will compensate each other, that is, the total action of these forces will be equal to 0, and the satellite is conditionally at an unchanged height relative to the Earth. By equating the two forces, we can then do the calculations. This formula will be the basis for describing the motion of any objects in the universe that rotate relative to each other. This is the form of motion that prevails in the universe, as you can see. The planet revolves around the sun, moving along its orbits, which are close to circular, maybe not exactly circular, but very close to them. And it is this motion that can be provided by the attraction of these objects to their gravitational centers. And when they're in their orbits, they're going to experience this dynamic effect, which is the effect of creating centrifugal force. A lot of phenomena that you may encounter in the tasks will be described with the help of this approach. The forces may change in their meaning. The formulas may change a little bit, but you'll always come across the same concept. It's the creation of a certain force to create a reason for the rotational motion. Let's not forget Newton's second law of motion and the calculation of the formula for centrifugal acceleration. This concludes our lesson. Goodbye.